Right. I'm not going to start with opening up DWSim because I want to go back to those heuristics 9, 10, and 11 because that has application. That has application for the TUT we're going to be doing today. So when we did the TUT 4, we had a reactor. It made methanol, and we cooled it down to 40 degrees C, which is the coldest we can do with cooling water. And we found we use liquid separation. This is not quite applicable because with heuristic mixture, if it is a liquid coming in, then you can just separate it. Okay. So it is heuristic 10 that we're talking about. That is what's happening in our, here we're making methanol and we are cooling it down to 35 degrees C, 40 degrees C in our case. And then we had a liquid stream and a gas stream, a gas liquid separator, and we went and put the liquid into a distillation column. And that is exactly what this says. Attempt to condense vapor mixtures with cooling water, then use heuristic 9, and heuristic 9 is this one over here. So that is select from distillation, enhanced distillation, stripping towers, and so forth. So we chose distillation. We put in a shortcut distillation column. In other words, we've cooled it down. We did a gas liquid separator, and we did a liquid. And that was where we stopped. So what we found, though, is in this vapor, there was quite a lot of methanol going missing because that vapor was just taken off the flow sheet. And now we're going to have a look at this this part of the heuristic, and that is separate vapor mixtures using partial condensers, cryogenic distillation, absorption towers, adsorption, and or membrane devices. And we're going to be doing an absorption tower. So so that means that we have our methanol synthesis reactor. We cool it down and have a gas liquid separator, and then we still have our original liquid separation system. We don't have liquid actually coming off this. Everything is vapor because we're operating at what was it, 250 degrees C or something, and we're going to put in this vapor recovery system over here. Okay, so it's a combination of the previous two flow sheets, heuristic 10, heuristic 11, and now we can get started with our DWSim. Okay, so let's file open DWSim TUT 4. Gibbs with a distillation column. Okay, that's fairly big. I'm going to just use control scroll bar to get it a bit smaller. Oh, what's this? It's already got an absorber on it. Oh dear, I've overwritten. Yeah, spot the mistake. Oh, I've got a backup. No, that backup will also have been overwritten. All right, let's file. File open, new process simulation model. I've got a feeling this is not going to work. Open simulation gives dist backup. This is not going well. Let's see if I've got two instances of DWSim now. No, just the one. All right. Delete. Delete yes, delete, yes, delete, yes. So what I've done, and I'm not going to take away this, I first moved this distillation column downwards and away from the gas liquid separator, so that I can put in a mixer, because the liquid stream that comes out of the gas liquid separator is what we want to, that will contain the methanol. So the absorption column is a column. Let me put it in, then I can start explaining. It's under columns, and it is an absorption column, and we're going to put it in over here somewhere. Let's put it in directly above this SC. Ooh. Okay, so with an absorption column, they haven't done the icon very well, but essentially you have to have a liquid coming in. So you've got a gas, and normally you'll have the streams coming from left to right. So you'll have the gas coming in here at the bottom, and it's going through upwards through the column, and it comes out at the top, and the required substances have been absorbed, and that required substance is methanol. So we're putting in our methanol rich stream in the bottom. It's the vapor stream. It's going up, and eventually when it comes out the top, because it's in counter current flow with water coming in, this vapor will only see pure water up here, and therefore all the methanol will be stripped out by the time this stream exits. So what we've got to do is actually put in a water stream, and put in where the water comes out, what that water contains, and then that water must come back here. So that will be MSDR 11, because the water that comes out the bottom will contain the methanol that we stripped out, that we've absorbed. Right, so let's first put in the water. Let me just show what I did here first. And I suppose some of you saw the TUT had been published, but essentially we had to change this to 1 bar. It was a 20 bar absorption, a gas liquid separator. And I only did that so that we would have a lot of dissolved gases in here that would illustrate how important it is to have a partial condenser when they're dissolved gases. So change that to 1 bar, enter, and this thing is operating at the right conditions. Put in your mixer, and you can link MSDR07, and then make this the feed to this column a new stream, in this case MSDR30. And then you should find that this part of the flow sheet will all be correct, will still be operating correctly. Okay, now we're going to go on to the absorber and adding the absorber. So click on the absorber, and here we're saying the number of stages is going to be 6, because 12 stages is far too many for what we're trying to do. In fact, even 6 is probably far too many, but never mind. And now we start going on specifications. There's nothing really to add. Stages. Okay, stages. Also, nothing to change. We're going to make each stage 100% efficient. And here are the 6 stages. We start with stage 0 at the top and stage 5 at the bottom. And that makes 6 stages. And now we get to the interesting stuff. Connections. Now have a look here. We've got a tab at the top with connections, and underneath that is stream connections, stream stage associations, side draw steps we're not going to bother about, but under stream connections we've got lots of things: feeds, products, duties, side draws, or these ones are not necessary. Products will be necessary. Now under feeds, no, I'm not going to do that yet, because I want to put water in as one of the feeds. So I am now going to rather go to streams, put in a material stream, and put it in up here where it's going to go into that column. MSTR12, but now once we've got this MSTR12, it's going to have equal quantities of every single component we've got. So let's go to compound amounts. See there 0.2 of each of these components that we've got. So I am going to make these 0. I always like to use tab, and that's a problem in this program, but in this case it's okay. And this one is going to be 1 and tab 0. And now we can accept the changes. And now we've got a water stream coming in. What I wanted to show is stream conditions. 3,600 kilograms per hour happens to be only just enough. I was trying 3,000 kilograms per hour, and I was struggling to get this thing to converge. So that is coincidentally, the default is just about the right amount of water to put into this column. Now we've got the water coming in, and we've got the water coming out. We've already made a stream called MSTR11, which is the water coming out. We need to put in the gas, and the gas is going to be this one. So we already got that stream, and we need to make a stream where the gas comes out. So that's another material stream that we must put in. I think it comes out somewhere down here for some reason. So that one we're not going to specify it because it's going to be a result of what happens in this absorber. Now we can start looking at the absorber again. So column feed port number 1. Now you see it's got 10 feed ports, but all that means is that where it's going to illustrate where the stream is actually going in. So it sort of divides this length into 10 bits, and if you choose column feed port number 4, then you're going to find MSTR going in diagrammatically in here, but it's not. In terms of the way it solves this, it doesn't matter. It's only how it shows on the screen. So let's put it in the top because that is how it should look. And we're going to put in MSTR12, the pure water. And I'm not going to go right down to the bottom because then it puts it in down here somewhere. So I'm going to use the second from the bottom. And it needs a few clicks before it eventually does that. And that is going to be vapor stream 9, VSTR9. Okay. And then that is the feed, and the products oh, it hasn't gone there yet. The products, the top product is MSTR 13. Nobody's commented. Okay, you just say good morning, and good morning to you too. So you're all with me here. Let's see how many people we've got now. 25. Bottoms product. Whoa, what's happened to that top product? The bottoms product is the water, which is MSTR 11. Okay, let's go and try this one again. Top product, MSTR 13. Maybe I didn't click it correctly. Okay, so yeah, that's all happened as it should. This one, it hasn't connected yet, but that's fine. Now let's think, is there anything we have to do, or can we say solve? Yeah, we haven't gone through all of these things yet. So that was stream connections, stream stage associations. So now it knows what streams there are, 2 feeds, a bottoms product. There should be 4 here. Let's go back to the stream connections. Yeah, this top product, it doesn't like MSTR 13. Keeps on going blank. Okay, thanks, Luca. Yes, as soon as I click on this flow sheet, then it goes blank again. Top product. Ah, no, we don't want this sort of problem happening here. I'm going to delete MSTR13. Yeah. And we will put a new one in and see if that helps. So go back to material stream, chuck in a new one, I'll put it up there just to be different. Click it. Okay, everything is okay. It's got a molar flow for some reason. But it's going to be calculated anyway. All right, let's try again. Okay, the vapor stream must go in at the bottom and must come out at the top as a vapor stream, MSTR13. Water goes in. We've already changed that to water. And that water methanol mixture must come down here and enter the shortcut distillation column. That is correct. Okay, I'll tell you what I'll do. I'm going to try, no, renaming won't really help. I've got a feeling the problem is that that MSTR13 has already been, it's already in the machine's memory, and therefore that's why it's got these numbers. The volumetric mass flow 3,600. That is normal. That's a good idea. Let's try that. So file, save as. That 5 lecture. Ah, yes, we have got 2 running at the same time. Why doesn't it show down here? No, anyway, never mind. Save changes, no. Okay. Right. Reload the DWSim. No, I don't want to update. And check it up there. Open that 4. No, that's that 5 lecture. Okay, and now we're going to try and add MSTR15 on connections, products, and here we want top product to be MSTR13. At least it's in a different order. If I click on it, yes. Ha! Who is that brilliant oak? Dean. Thank you. Okay, so then I think we've done everything we need to. You see what I mean about taking this thing down here somewhere? It's a silly place to put the outlet. So wait, we might not be finished yet. So I just wanted to check the. We aren't finished yet. Stream stage associations, right? So the stage location for MSTR12 is stage 0. And the feed down there at the bottom is stage 11. They don't use the bottom stage. They just say something below the bottom. That's why they use this number 11. I think it's rather strange, but that's the way it is working. And I think we have then done. We're not going to do side draw specs. We've done stages. There's nothing on estimates. When I was desperate trying to get 3,600 kilograms per hour water to work, I did enter some estimates. Look at these funny estimates that it starts with. I'm going to change it anyway, because the water's coming in at 25 degrees C. So I'm just going to leave all of them at 25. It's a much better option than starting at such a low temperature at absolute zero. Okay, so I think we have done everything. That the stages, efficiency of 1, specifications with blank, absorber 6. So under connections, this is where we've got stream connections, feeds, products, duties. We're not going to fit that. We're not going to do stream stage connections, associations. There is only the one thing, and then we are done. Right. So let's try and run this flow sheet. Phew. Fingers crossed, as Dean says. All right, so there we go. Now, I want to have a look at this stream. I want to see how much methanol is flowing in this stream, and I want to get it in kilograms per hour. So I'll look at this side, results. Instead of mole fractions, I'm looking at mass flows, and I want to see how much methanol is coming out there, 197 kilograms per hour. Now, let's have a look at how much methanol we've got in this stream. MSTR07, results, mass flows, and methanol, 300. So you can see it's almost, I mean, like it's more than half of the amount that we got out of stream 7. It would have gone missing if we just let the stream go out. Let's have a look at MSTR13 and have a look at how much methanol how much methanol we're losing. Mass flows, and we look at methanol, and it is 0.02 kilograms per hour. So the absorber is obviously working very well. We are losing a fair bit of water, but not that much. But the main thing is carbon dioxide. So if we go to mole fractions, and we look at how much carbon dioxide there is, it's 0.71. So that's essentially what we're losing out of this process. Is mainly just carbon dioxide. And there's a bit of carbon monoxide, so you'd have to stick this thing through a flare, because otherwise it'll be a dangerous gas. Alternatively, you can do a split, a purge of the stream, because you've got to get rid of the CO2, and then you can put back to the Gibbs reactor, to the water gas shift reactor, so that you can make use of the CO at least. CO2 plus, what did we put in? Never mind. So it is possible to recycle the stream so that you don't lose anything. These are, let's go back to in MSTR 13, mass flows. And that is quite a lot. 280 is quite a lot compared to the 3,600 kilograms per hour that we put in here. You can see there mass flow at the material stream. I can't move my cursor to show you, but there we go. 3,600 kilograms per hour of gases coming in. They are carbon monoxide and water, and we're losing 280 of carbon monoxide. So we would like to recycle that it'll probably be worthwhile to do a purge and recycle some of the carbon monoxide. Okay, what else is there? Yeah, and finally you could look at this one, and we look at mass flows again. No, it doesn't matter about the labeling. I label them because when you delete streams and then you add new streams, it sometimes renames streams with identical names. Now, in memory, it might be a different, it'll be a memory address that refers to that stream, and it won't be referring to that with a number. But if you want to say it is MSTR, let's say it is MSTR 13 that is connected there, and there's another MSTR 13 named over here, then you as a user can't tell it use that one, not the other one. So that's pretty much why some of these are labeled LSTR and then VSTR because it was mixing up it was having duplicate names at one stage. All right, so I just wanted to have a look at this one and look at the mass flows again. And there's all of our methanol. Now you can have a look. There's a nice 467 kilograms per hour of methanol and 2.7, only 2.7 of water in there, which is going to be a small amount. And look how little of anything else. The only major contaminant there is CO2. In fact, CO2 is more than the water. So that's not an issue. So let's have a look at mole fractions again. Carbon dioxide. So as a mole fraction, it's how can this be? Oh, this is 10 to the minus 6. 98% methanol and 0.8%. No? Yeah, 0.8%. Carbon dioxide. So decent specs, and that's what's nice about this shortcut column, because it designs the column according to your specs of how much is the heavy key and how much is the light key. All right. Any questions? Did anybody try this at home? I should have sent out an announcement that it was ready, but oh well.
Prof, I just want to ask, why do we reduce the pressure of the vapor liquid separator from 20 bar to 1 bar?
Because we want to get off as much of the gas as possible. We don't really want the dissolved gases. We don't want dissolved gases in the stream. So if the pressure goes from, essentially your water and your methanol flow remains the same even if you increase the pressure, but what happens is the more of the dissolved gases dissolve in this liquid. And when you've got dissolved gases, you've got to have a partial condenser, and then you don't get such good separation. So you want to essentially get rid of gases as quickly as possible. And when you do that with 1 bar, you'll find that I don't think it makes much difference over here. Let's have a look, for instance, at methanol in this stream. We did have a look at it. Fractions, mass flows. Methanol is 353. I'm just going to write that one down. 353. Water is 1014. Now let's go and change this one to 20 bar. Like that. So it did calculate that correctly. Let's just have a look at this one. It did calculate this one correctly. So let's go and have a look at the mass flows. A little bit more water. and a lot more methanol. So it does help. Yeah, good question, Philip. Helps a lot more than I expected. That's probably because you see the water didn't change much. So the fact that the methanol did change a lot is to do with 40 degrees C for this stream. Let's just check if it is 40. Well, we're operating this GL separator at 40 degrees C. So at 40 degrees C, the boiling point of methanol is 66 or something like that. So it's very close to the boiling point of methanol, and that's why we're losing so much methanol out there. If we've got 20 bar, we can liquefy much more of the methanol because we were close to the boiling point. So that's pretty much the reason that it's so sensitive to that pressure. Normally, you would not expect it to be. If that were ethanol, it would not make such a big difference. So anyway, that's a good example of what design is about. You know, what do we choose there for the pressure? And maybe neither 1 bar nor 20 bar is the correct one, is the best one. So let's have a look at MSTR11 and see what flows we've got. Doesn't have results. That's why it's red. All right, that's why. And I'll tell you what we'll try and do to fix this one at 20 bar is we'll try and increase this to 3,000, 5,000. Why is it not changing? 5,000, enter. Yeah, you see, it's very sensitive to that particular metric. So then we can get this thing to solve if we use a higher flow rate there. Any other questions? Oh, wait, found your error. There we go. Yuri. Oh, okay. Feed stage is mixed up.
Prof, you also say in the PDF that we can split the liquid stream coming off from the distillation column and then send the water back. Do we use a vapor liquid separator there, or?
Yes, no, gas liquid separator, same as this one. No. You won't. You use a mixer splitter.
But then we will send methanol also back with that water.
You're sending it in here, yeah, which is good because there is some water, but not much. So I'm just going to add the inlet stream is now MSTR09. And we're going to make a new outlet stream. Well, the inlet stream, outlet stream 1 is MSTR12. And
you also said we should first cool that stream to 40 degrees centigrade.
Yeah, you're right. Yes, because it's at quite a high temperature there where it is now. Yeah, let's start again. If I just choose it and delete it. Yeah, that's fine. Exchanges, a cooler has, let's first choose it. It has an inlet stream called MSTR09. And it has an outlet stream that we want to create. And then we want to put in a splitter. Stream splitter. Actually, I want to put it a little bit further away. And we want to connect that stream, which is STR14. I hope we don't have identical names again. No, we don't. STR14. We want to, oh, and the other one of the outlet streams is MSTR12. And the other outlet stream we want to is the purge, MSTR15. And then we're going to choose the split ratio. So let's have a look where we can do that. Stream, split ratio, stream 1. It's not a ratio. I want a mass flow spec. And stream 1, mass flow spec, I want to make that 5,000 kilograms per hour. Enter. Okay, you can solve now. He said, hopefully. I might have to F5, but I think I've got everything right. We haven't cooled it. Heating, cooling, kilowatts. There we go. Outlet temperature. That's rather nice. But we're not going to be able to get to 25 with cooling water, so we choose 40. And input string was not in a correct format. Input string. Kilograms per hour, that's a number. So that's the right format.
I think you should just add an energy stream to the cooler.
Thank you, of course. Ay, ay, ay. Ah, stupid. Remove. Where's the energy stream? Oh, that's the splitter. The energy stream to the cooler. Oh, yes. Energy stream, add it. And yeah, press F5. It won't like it because MSTR16 is still showing. Oh, yes, I only disconnected it, but it didn't delete. Yes. And let's try again. So flow sheet. F5 key, yeah. So Philip, did you have trouble with this thing? Did you try it?
Yes, Prof. I'm struggling to get the splitter to actually split the streams.
Yeah, let's have a look at this one. It is 5,000 kilograms an hour. This one. Difficult to see, so I'll just move that up there and have a look. It is 145. Yeah, sounds about right. But you did use this spec that I suggested, that you make it stream mass flow specs.
Yes, Prof.
Okay. But certainly this would be the way to go because any that small amount of methanol, this 1% methanol that's in the stream, is going back, and therefore it will eventually come out. It can only come out there because 1% methanol over there is a much smaller stream. So we would certainly get, if this thing would solve. Script data successfully, and let's try solve flow sheet. I wondered, you see, it's not actually going and solving this bit, so I'm going to try this force.
Wouldn't this need a recycle block for the logic?
Oh, very good point. Who is that? Who is that said that?
Well, it was Eugene who recommended the idea, but it's just in the comments.
Excellent. Okay. Right, so let's do that quickly. Seeing we got the time. So we go and find logical ops, recycle block. Rotate it minus 90 degrees. Wait a minute. It's minus 90. Plus 90? Oh, this minus or greater than. Okay. I hope that's right. So anyway, click it, inlet stream. All right, I'll have to create an inlet stream. Got that wrong. Oh, yes, and I got this one wrong as well. I have to rotate that one also 180. So this one connects to MSTR instead of 12. It's now connecting to 16. And the other stream, the exit stream, is MSTR 60 is 12. 12 is down there. And that's our recycle block, which has got an upside down R. Right, and let's try and solve that. No, it's not much good. Yeah, this thing is not happy with me because if I force a solve, then it crashes. But anyway, Philip, this is what you should do. You just got to figure out what's going wrong.
Okay, thank you, Prof.
All right, guys, any other questions? Stream outlet, yep, that's great. Okay, guys. Yeah, have a good break. And I'll see you Monday week. Stop the recording.